Okay, class, welcome to lecture 20. So today we are going to talk about functions more, but what we're going to do is we're going to focus on especially nice functions. And, oops, especially, I don't know how to spell that. I'll just say very, very nice functions. So these are functions which have additional properties. That's what it means to be very nice, I guess. It just has more nice properties. So first I'll display these nice properties before saying these fancy words on the title. So remember last time we could sort of see how a function works by just drawing little dots and arrows. So the dots represent elements in these two sets, and arrows represent the function definition. So this is a especially nice kind of function in a very specific way. And that is, if you look over here, it's sort of like there's a copy of the first set inside of the second set. And what's going on is there's no like overlap. So no two elements go to the same place. And this is an especially nice property because it sort of creates a copy of the first set inside of the second set. As opposed to something that's not like that, it would be something like this. So here, this dot is coming from two different places. So there's sort of like this overlap going on. Okay, so that's one nice property, is not having any overlap. And then the other nice property is being able to cover up everything in the codomain with your function. So that means something like this. There might be overlap, so we don't get that nice property, but we get this other nice property where everything over here, all elements come from using the function, aka they're all in the image, if you want to think about image from last time. So as opposed to something like this, here we don't get this property because we don't have any way to hit this element. Instead, this is like that, the first property where we don't get any overlap. And then if both properties happen, it's like the best possible function. So there's no redundancy, there's no overlap. So element goes to element goes to an element, and you are able to cover up everything in the codomain with your function. So that's like both properties happening at once. That's the best type of thing. Okay, so of course we have to describe these properties in a very fancy way, and we have to use fancy math words and fancy definitions to be very precise. We can't just draw fun pictures all the time. Okay, because pictures don't represent all possibilities. So let f be a function from a to b, as we are talking about functions. And these properties are about functions, so you can't ever say like a set is one of these things. You can only say a function is one of these things. Okay, so let f be a function. Then f is called injective, very fancy word. The less fancy version is 1-to-1, but I'm going to use the word injective. So it's called injective when that first thing happens. So in pictures, it's the one where there's no overlap. But how do I say that in a very mathy way that accounts for all possibilities? Like this. It's going to seem weird at first. So whenever you have two inputs, so actually I'm going to, because people like X to be their inputs, I'm going to call them X1 and X2. So whenever you have a pair of inputs, meaning they're in the domain, if you plug them both in and they go to the same output, well, that would be bad, right? Because we don't want that. We don't want two things to go to the same thing. But if that did happen, when would that be okay? If it turned out, sneakily, that those first inputs were actually the same the whole time, then that's fine. If these two guys were actually at the same point, then you're just saying that one thing goes to one thing, instead of saying that two different things go to one thing. So it's a very strange definition, but this is what it means to be injective. So let me just try to rephrase this. So this is saying that whenever you have two supposed elements, two elements give you two outputs, two elements in B that are the same. Whenever that happens, it turns out that those two inputs were actually the same the whole time. So this is really saying exactly what we want. This says that that each f of A only comes from one element A. This is really saying the same thing. Because what you're doing is you're pretending that you're able to get f of A in some other way. I'm just changing the letters now. But then it turns out that that means that actually A1 and A2 were the same input the whole time. So the only way to get that output is with that input. And there is no other input that gives it to you. And then you could take the sort of the contrapositive of this definition and say it like this instead. And this one sounds a little bit more logical. It sounds a bit more like what it should sound like. So if you have two inputs and they are not the same, then they should go to two different places, meaning that the outputs should not be the same. So this is saying the same thing, and it does sort of sound a little bit better. It's saying if I pick two different inputs, then no matter what, I'm going to get two different outputs. And that's saying exactly the fact that you're never going to have a situation like this. And that picture is really what it means to not be injective. Okay, but so if this definition of injective sounds so much more logical and makes more sense as to why this picture is happening and this picture is not happening, and why do we use this definition instead, which sort of sounds a bit tougher? It seems sort of backwards. You start with the outputs. If the outputs are the same, then they must have come from the same place. It's because this definition has equal signs in it, and if you have a lot of practice with proofs, it's easier to work with two things being equal than it is to work with two things not being equal. in a proof. If you know two things are equal, usually you can do stuff after that. If you know two things are not equal, well, there's a lot of ways for things to not be equal, so it doesn't really narrow down much for you. Okay, so that's why when we prove things are injective, we're always going to use this definition. Okay, so again, it sounds like a tough definition to work with, but it just takes a lot of practice and it won't be so bad, I promise. So let's do an example. So I need to have a function, and we're going to try to show that it's one-to-one, aka injective. So it's going to be defined by, so this is a nice function because I'm not just saying where everything goes, I'm saying the whole rule all at once, so it's a little bit easier to work with. Okay, so how do I show that f is injective? I'm just going to show a definition. That's how proofs work. I'm just showing a definition is true. So what do we need to show this is injective? We need to show that no matter what two inputs I start with, and you could use whatever letters you want. So this time I'll use A and B. So no matter what two inputs you start with, aka things in the domain. So the domain and the codomain are both R, but I'm really picking this R when I say this, because I'm picking two things in the domain. No matter what two I pick, if they go to the same place, then they must have come from the same place. They must be the same element of the domain. So this is what we need to show. So to do a proof like this, well, because I'm trying to show a fact about two arbitrary elements, I have to let two arbitrary elements into existence so I can talk about whether the fact about them is true or not. So that's why the proof will start like this. Let A, B, B, and R, or whatever your two favorite letters are. Then I'm trying to show an if-then property about these two letters, which means I have to assume the if part. So I'm going to assume f of A equals f of B, and then I'm going to show A equals B. Now this little setup is sort of your guideline to all the proofs about being injective. This is how they'll all work. What's going to change is the sets that you use. It could be a different domain instead of R. It could be something else. I'm going to put that star there. But that's it. Everything else will be the same. What changes now is you have to take what you've assumed and expand upon it until you get over here. And f of A equaling f of B means different things depending on the function. This is the function for this problem. So what we can say is just exactly what this is, which is I'll just plug A in and I'll plug B in and I'll pretend they're equal. So 3A plus 7 equals 3B plus 7, right? Okay. And I have to show A equals B. Well, all I'm going to do is solve this for A and B and hope things work out, and they do. Subtract 7 on both sides, divide by 3. So F is injective. Now, what can change in a proof like this is this step can become much harder if in fancier proofs. Okay, but that's it, not so bad. So let's see something that's not injective. So this will be defined by x squared is not injective. So to not be injective just means that two elements do go to the same place. And so you're giving a counterexample to the fancy definition by saying that there do exist two numbers such that even though they go to the same place, they are not the same number. They are not the same input. So there's lots of counterexamples. So I like this one. Use a equals 3, b equals -3. So then f of a is 9, f of b is 9, but 3 does not equal -3. So two different elements go to the same place, so it's f is not injective. Okay, that's typically how counterexamples will work for injectivity. So let's move on to the next definition. This one's a little bit easier to get a handle on, I think. All right, so let f be another function. Again, this is a property about a function. So the function f is called surjective. It's not exactly the opposite of injective, but they are dual to each other. If you know what that means, then you shouldn't even be watching this video because you already know too much math. But surjectivity is dual to injectivity. And the less fancy way to say surjective is onto. If, so this just means the other picture that we drew, everything over here gets hit. And you don't care if it gets hit more than once, it just has to get hit. So how do I say that in a fancy math way? Well, what I'm doing is I'm talking about things in the codomain. So, and what I'm trying to say is that all of them get hit. So I'm trying to say that for any b in the codomain, there exists, use a, there exists an element in the domain that can hit it. What does that mean to hit it? It means when I plug it in, I get to b. So this is saying that everything in the codomain, there's a way to get to it from the domain using the function. And so this definition sort of goes along with the picture a little bit more easily than the other definition, the injective definition. But yeah, this is just saying everything gets hit. So I'll draw a better picture here. So this guy is surjective because no matter what b you pick, you can find a way to get to it. Whereas this one is not surjective because I can now find a b, something in the codomain that does not have a element getting assigned to it. Okay, so let's show that we'll talk about the same function. So I guess it was 3x plus 7 is surjective. Now, interestingly, the definition of surjective is easier to understand, but harder to prove things are surjective. But it's harder to prove things are surjective. Whereas the definition of injective is harder to understand, but there's sort of a recipe for the proof. So it's actually easier to prove things are injective once you understand the recipe. A surjective proof really does take lots of scratch work. Because the idea is it's an existence proof. You're trying to find a way to map to a number. So over here, I'll write what we're going to do. Need to show for any b in R, and now I'm talking about the second R because I'm talking about the codomain, that there's a way to map to it from the domain. So now this R is that one. So what that means is to start this proof, I have to think about an arbitrary element of R, of the second R. That's how a surjective proof starts. Let B be in the codomain and find an element in the domain such that when you plug it in, you get the element from the codomain. And of course, I can't just literally go through every number and check this. That's why you have to let this happen so that you're doing this arbitrarily for any real number. If you pick 5, then you've only done it for 5. So you let B be an R and find an arbitrary way to make B pop out using the function. Which means, basically, that you need B to be the result of doing 3 times something plus 7. So that something is what I'm calling A, but I don't know what it is yet. So the trick is just solve for it. Minus 7 divided by 3. So if I let A be that, then when I plug A in, I will end up with B just like I wanted. So that's all scratch work to make it work. Okay, so you secretly find the A on the side with scratch work, and then in the proof, it's magic. So you just say, consider this, and then you show that it works. Then f of A equals f of B minus 7 over 3. And now I actually use what f is. It's that 3 times B minus 7 over 3 plus 7 equals B minus 7 plus 7 equals B. So what we've really done is we've constructed a recipe to create B no matter what B you start with. And that's how this shows f is surjective. So the idea behind this is, give me your favorite number. What's your favorite number? 10? Okay, then I'll tell you how to make 10 pop out. Just plug in 10 minus 7 divided by 3. And I can do this for any number you can think of. So that means I can do it for any number. So I can get anything in the codomain using this little recipe of just taking whatever number you want, subtracting 7, dividing by 3. And so since I can do it for every number, that's what shows f is surjective. Okay. So now, the last definition is sort of the easiest because it's just a combination of the previous two. So if your function is especially nice, it'll be both injective and surjective. So then f in that situation is called bijective. So if f is both injective and surjective. So it looks like we just proved that 3x plus 7 is bijective because we just did both proofs. So I'm not going to reprove it, but if you wanted to prove it from scratch, you would show both. And what this really means, what it means when both happens, when both things happen, is that the picture will always look something like this. Because nobody goes to the same place as anybody else, all your arrows sort of just have to go to separate things. But then, by virtue of it being a function, there has to be arrows out of every single element. And then by virtue of being surjective, everything has to be hit. So this is a bijective function. But in fact, every bijective function is going to basically look the same, just with different things. And of course, you can have two different bijective functions or more than. So for example, if I actually name these things, I call this like x and y, a and b or something, that's the function that turns x into a, y into b. And it is a bijective function, but I can like do this instead. Still a bijective function because I'm still sending, each element is only getting hit once on the right and everything is covered. So there are lots of bijective functions between two sets, but they sort of all look the same. So this could be a different one here. Okay, that's the idea behind bijective functions. If your sets only have finitely many things in them, things are a little bit trickier up here where the domain and the codomain have infinitely many things like the real numbers, but we'll deal with that later. Okay, so let's think about more functions real quick. So how about this function? F from R to, instead of R, I'm going to use this interval notation. So interval notation actually just describes a set in a very quick way. This is really the set of real numbers such that x is greater than or equal to 0. And the reason that people don't use interval notation is because what if I wanted to say that? Well, then it sort of looks like an ordered pair, and it's not. So that's why I'm going to tend to avoid interval notation. But here it's okay, because of the bracket, it's more clear that it's an interval and not an ordered pair. Okay. So let's define this by f of x equals x squared. So this one, we already sort of said earlier, but we were going from R to R, is not injective because f of 3 equals f of negative 3. Sorry, not injective, but it is surjective. So to be surjective means I need to find a way to hit everything in the codomain. So given some output in the codomain, what do I plug in to get it? I just use the square root of y, because then f of x will be f of the square root of y, which will be square root of y squared, which will be y. So if I want 26 to pop out, I just got to plug in square root of 26. So it is surjective, not as formal of a proof, but that's the idea. But I can use the same function, and if I change the sets around, I can change what happens. So for example, if I go from 0 to infinity as my domain, and I make my codomain R, I use the same function x squared, now it's injective instead, but not surjective. So the opposite of last time. Why is that? Well, now it's injective because I'm only plugging in positive numbers. So if f of a equals f of b at this point, that means a squared equals b squared. A and b, they're both positive or zero numbers. They're not negatives. So that means that when I square root both sides, I'm not having to worry about a plus or minus because those were not being plugged in the first place. So now a does equal b. So it's injective. Whereas if the domain was all real numbers, then I could get a equals negative b instead. Okay, and now that I've changed the codomain, it's no longer surjective because I can't hit every real number. I can't hit any negatives with x squared. So for example, if I have negative 10 in the real numbers, there does not exist any number in the domain that I could possibly plug in to make a negative 10 pop out, because I would need this to be true, but it's never true unless I bring in imaginary numbers, which I did not in the domain. So that's why it's no longer surjective. Okay, so I want to do one last big proof, just for extra practice of showing injective and surjective. And I'm going to get even fancier. I'm going to do a function from a product to another product. I'll use my other fancy notation. So where is my ordered pair going to go? It's going to go to, it has to go to another ordered pair. And the first ordered pair will come from doing 2a plus b. The second ordered pair will come from a minus b. So we're going to show that this is bijective. Okay, so we're going to do injective first, because that one is actually more straightforward, even though the definition is a bit more confusing. And the way that works is I need to let two guys be in my domain. But this is a bit weirder because they're both going to be ordered pairs. So in this situation, I have to actually say a little bit more about what it means for them to be in the domain before I continue. So x1 is going to be some ordered pair. And x2 is also going to be some ordered pair. Okay, so now to show injective, we assume that when I plug them in, I get the same thing. And then I show that they were secretly the whole time the same inputs. It's like that movie, The Sixth Sense. The guy was dead the whole time. He just didn't know it until the end. Okay, so when we assume this, that's where we go from when we try to get to here. So since f of x1 equals f of x2, I'm just going to expand upon that. What does that mean? Well, x1 is really just an ordered pair, and so is x2. And f is a function, so I can just say what the function does to these ordered pairs. So it turns the first guy into 2a1 plus b1, comma, a1 minus b1. And it turns the second guy into 2a2 plus b2, comma, a2 minus b2. Now, what does it mean for two ordered pairs to be equal to each other? Remember, that means that they have the exact same coordinates. So that means that this guy's x coordinate equals this other guy's x coordinate. And this guy's y coordinate equals this other guy's y coordinate. Now we have a system of two equations. So it's a little bit more complicated showing what we want to show. We want to show this thing. Sorry, no, we don't. We want to show x1 equals x2. Those are just coordinates. Those are ordered pairs. That means we really need to show a1 equals a2 and b1 equals b2 using this little system. And it's doable. It's going to be a little annoying, but we can do it. So let's add the two equations. Remember doing this, 3a1, those will cancel, equals 3a2, those will cancel, a1 equals a2. Okay, then substitute back in. And then you'll get b1 equals b2. So a1 comma b1 equals a2 comma b2 because a1 equals a1 and b1 equals b2. So that's just x1 and x2. So f is injective. So again, the path from getting to here from here was a little bit longer, but it is very sort of algorithmic or systematic. You just expand upon what the initial equality tells you. But when we want to show f is injective, or sorry, surjective, It's a little bit harder. I want to let something be in the codomain. Then I got to find something in the domain such that when I plug it in, it gets me to that element. So again, we're talking about coordinates. So since y is in r cross r, I can actually say a little bit more about it before I proceed. Y actually just looks like some a comma b. And this x that I'm looking for also lives in r cross r, so it's going to end up looking like something comma something too. But this is where the scratch work comes in. So I need f of something to equal a comma b. So I don't know what that something is yet, so maybe I'll just call it C and D. And then I'll be sneaky and I'll just pretend C and D are correct and use the definition of the function way up here to figure out what they should be afterwards. So 2a plus b, a minus b. So 2c plus d, comma, c minus d. So I'm really trying to figure out what c and d are in terms of a and b. Because the idea is I would already know that I want to get like 5 comma 10. So I'm trying to figure out what I should plug in to make 5 comma 10 happen. And so what I plug in should involve 5 and 10 somehow. So now C and D should be solvable in terms of A and B. And they are, because this sets up another little system. Because I need the coordinates to be equal. So then I can say lots of stuff. One thing is I could say that C equals B plus D, and D equals A minus 2C. So then I could plug that in there, and I can get C in terms of A and B only by doing that. So let's see. So then I add the 2C over. So what this is saying is if I want A comma B to pop out, then what I need to plug into the first coordinate to make that happen is B plus A over 3. And then I can plug that back in to get D. So I could plug that in there if I want. And so this will make A and B pop out if I plug this in for C and D. Okay, so now I can put that in the proof. All right. So consider x equal to, so the first coordinate I said needs to be B plus A over 3. The second coordinate needs to be A minus 2 times that. Now I just have to show in my proof that it'll make Y pop out. It'll make A comma B pop out. And it will, because that's what the scratch work was preemptively showing us would happen. Okay, so I plug it in using the definition of the function. The definition of the function is to do 2 times the first coordinate minus, was it minus? Where did I write it down? No, plus the second coordinate comma the first coordinate minus the second. Looks all very complicated. And we should just get A comma B after all this work. let's see that happens. So what happens here? I get 2b plus 2a over 3 plus, get a common denominator here, 3a minus 2b minus 2a over 3, comma, okay, this one needs a common denominator 2, minus 3a over 3, minus 2b minus 2a, like that. You could do this algebra however you want. Doing algebra in front of people is embarrassing. Don't judge me. Okay, so let's see, 2b plus 2a plus 3a minus 2b minus 2a over 3. Looks good so far, I think. b plus a minus 3a. Distributing that negative through, plus 2b plus 2a over 3. And over here, what do we get? So 2a cancels with 2a, that cancels with that. 3a over 3, great. What's going on over here? 2b. Oh, good, okay. A plus 2a is 3a, minus 3a is 0. So I just get 3b over 3. Ah, wonderful. Equals a comma b equals y. So I found a way, no matter what element I start with wanting to pop out, wanting to get hit by the function, I found a way to make it happen. If I start with y equaling ab, some coordinate, this is what I plug in to make that happen. Okay, so that shows f is surjective, so f is bijective because we did both. Okay, so that ends the proof and that ends the lecture. See you next time.